My name is Rohit Karlupia. I work as a technical director at Qubole, and I'm the author of Sparklens. And in this presentation, I'll basically tell you how Sparklens really works and how can you optimize your applications using Sparklens. All right. So the first thing that I want to talk about in this presentation is that it's really easy to use Sparklens. There is nothing that you need to install. There is nothing that you need to download or compile or nothing. All you need to do is that when you run your Spark Summit or Spark Shell, just set these two parameters. The one is packages, and the package that you want to use is Qubole Sparklens. And the other parameter is the Spark extra listeners parameter, and the value for that is com Qubole Sparklens Qubole job listeners. Don't worry about it. This is something that you can easily find out again. So that's it. That's all you need to sort of do to get your Sparklens report, and it could be like anywhere. It doesn't really matter if you're using Spark on cloud or are using on-prem or on local laptop. This will work seamlessly wherever you use it. Apart from these two parameters, there's another parameter that you can add, and which is Sparklens report email, and set your email address. And what it gives you is that instead of just getting a console text report out of Sparklens, you can get a very nice HTML report, which is pretty easy to share and and discuss. So you'll get an email like this with a link to your report, and it will be very easy for you to really go through, look at your report. So with that like out of the way, I'll start talking about what exactly is Sparklens and how you can use Sparklens to debug or optimize your applications. So usually when we talk about optimizing our applications, Spark applications, typically there are two main goals. Either the goal is that we want to reduce the amount of time the application takes, or we want to make it optimal, maybe make it work better with less resources. So what I'm showing you on this screen is essentially a timeline of a Spark application. So if we look at on the top row, there's a driver, then we have some time, then stage one, stage two, stage three. These are essentially how a computation sort of gets executed on Spark. And then if you look at other rows, they are labeled core 1, core 2, core 3, core 4. These are the cores on which some tasks are getting scheduled. So in this example case, we can see that there's a driver running. There are 3 stages, and each of these stages have some tasks. Stage 1 has, for example, 4 tasks, 2 has 3, and stage 3 has 2 tasks. And the time is flowing from left to right. Now, what is interesting to see is a lot of white space on this particular screen. And this white space basically refers to a time when the core was available, a compute unit was available to be used, but there was no task which was using that compute. So one way to sort of optimize our application is simply looking at reducing all this white space. So if we can remove this white space, we can essentially reduce the amount of time, compute time that is getting wasted, and make our applications much more efficient. So let's try to find out what is this white space composed of. So this is too colorful a slide, and what you see here is a division of this time that is compute time that is getting wasted. So there are 3 main ways where this time, this white space, or this compute time is wasted in a distributed application like Spark. These 3 are wastage because of the driver, wastage because of Skew, or wastage because of lack of task. So let's go through each one of them in detail. If you look at the driver column, there are like 1, 2, 3, 4, and 5 driver columns. You will see that below driver, we always have this orange color. This orange color essentially comes from the fact that when a driver is running in Spark, the executors simply wait for their next set of tasks. And when there are no tasks, executors cannot really use the compute. So if you have an application which, let's say, finishes in about 10 minutes, and of those 10 minutes, 5 minutes is used by the driver, then the chances are, then essentially what it means is that 50% of your compute resources are actually getting wasted. So one way to simply make your applications faster or better or more scalable is to simply reduce the amount of time which is spent in the driver. The next major contributor towards this compute wastage is the Skew. Now, if we just look at stage 1 and look at a couple of tasks, the task 1.1 roughly takes about 2 units to complete, whereas task 1.2, 1.3, 1.4, they finish in about 1 unit of time. Now, what happens is that when these 4 tasks are running or started concurrently, after 1 unit of time, the three tasks will be complete, but the fourth task is still sort of going on. The way Spark work is that it will wait for the full stage to complete before the driver will kick in, and that is why the time we see this red area in stage one, which is essentially the time which is getting wasted because of the skew, because the computation cannot move forward to the next stage until we have finished all the tasks of a particular stage. So that's the second part, which is essentially the skew. So the main thing to learn here is that if there is a lot of skew in your application, or in terms of the time that a particular tasks take in a given stage, then it's very hard to make that kind of application really efficient. The third thing that we can look at is the lack of tasks. So the yellow area, for example, in stage 2 and stage 3, refers to the problem of not having enough tasks. So stage 2 only has 3 tasks, and our for example, this our dummy application has 4 cores. So with 3 tasks, you cannot really utilize the 4 cores. So unless you have enough tasks, it's not possible to be efficient, be at least not waste resources. So the only way you can use 4 cores is to at least have 4 tasks, and that's the problem that is shown by lack of tasks. So all right, so now we talked about how the compute is wasted along 3 dimensions, and how we can sort of at least uh, understand it and try to sort of find some solutions how to uh, how to reduce these factors. Another thing that is very important to understand when we talk about the Spark applications is that typically people have belief that if we throw enough resources, then the application will run faster. That belief is actually not true. So if you look at this particular application, that the dummy application that we have, we see that there is some time which is spent in the driver, and then there is some time which is spent on the executor side. If we look at the driver side, we can see that adding more executors to particular to let's say Spark application cannot make the driver really run fast. No, driver is doing some computation, and that computation can only happen on the driver. So adding executors cannot have any impact on how much time does the driver takes. So that's one. So that is the time that we cannot reduce by adding more executors. There's more to it. Now, if you look at stage one, no matter how many executors we add give to stage one, the minimum amount of time that a stage will take is bounded by the longest or the largest task that is running as part of that particular stage. So essentially, you cannot make a stage run faster than its slowest or the longest task. That is true because task is indivisible. So when you add more executors, you don't divide the task. The task lengths remain the same. The only thing that you get is that because there are more executors, the task can span or use more resources. So not so irrespective of, so essentially what it means is that if we just sum up these two numbers, one, the time spent in the driver, and the time spent in the longest task of each stage, and what we get is something that we call the critical path. And that essentially is the minimum amount of time that Spark application will take, even if you give it infinite resources. So having this number, knowing what is the critical path of your application is a very important number in front of you, because you can compare it with whatever is your real runtime. If this critical path is very, very close to your real runtime, what it means is that you really cannot you cannot give more resources and expect your application to run faster. It's almost at the verge of what do you say, at its scalability. But if the critical path of your application is much lower than the real whatever number that is are you measuring your total runtime of the application, it means that if you throw more resources, you can actually make it run very fast. So difference between critical path and real runtime is actually the real elasticity of your application. So I mentioned about when you send a report, when you pass those 3 parameters, you'll get a report, Sparklens report, and a link. So I'll just talk about what does Sparklens, what kind of things Sparklens will report to you. So the first thing that Sparklens will report to you is the driver overclock time. As we discussed, knowing how much time is being spent in the driver versus how much time is spent in the executor is very important, and we need to minimize the time spent in the driver because it leads to pure wastage. The second thing that Sparklens will tell you is the critical path. As we discussed, like in the last slide, knowing the critical path and the actual runtime and the difference between the two is very important to understand. Will your application really scale if you add more resources or not? The third thing that's on this slide is essentially how much of the compute resources that are given to the applications are actually not used at all. So knowing that the compute is getting wasted is very important for you. So based on that, you can figure out, there is a problem, there is a potential cost reduction or latency reduction that you can do if you spend time fixing these problems. So another thing that Sparklens will do for you is a simulation. So Sparklens basically gets very fine grained data from the Spark application. So it, for example, knows uh, each for all the stages, what is the dependency structure between them. It knows all the tasks, when they were started, when they finished. So using this detailed information, what Sparklens does is that it can simulate how your application will run if you change the number of executors. So for example, let's say you have an application which, let's say, takes 6 hours to run, and maybe use, let's say, 100 executors. Now this will be a pretty expensive application, and if you want to optimize it, and you want to do it by trial and error, the chances are that if it takes 10 retries, then you'll be spending maybe 5 days just getting to find the right number of executors that should be used with this application. With Sparklens, it's not really required, because you just take one run, and Sparklens can sort of simulate and tell you how this application will behave as the how much will be the runtime, for example, of the application with a different number of executors. So in this particular graph, for example, we can see that this application, if it runs with 24 executors, will finish it about 11 minutes. But if it is run with 1245 executors, it will finish in 4 minutes. Now, for some people, this is probably a very bad trade-off. They will probably be okay with just letting it run for 11 minutes, but for some, they might want it to finish in 5 minutes or 6 minutes because of different business constraints. So knowing upfront what are the trade-offs available in terms of cost and latency helps people make better decisions. The third thing that Sparklens will give you is a report like this, which basically tells you how many executors were available to your application at any point in time, and also how many executors were actually required. So even if the executors would have been this much, it would have finished in the same amount of time. So the amount of white space that you see sort of tells you that maybe you have over allocated resources, and it will be a good idea to sort of reduce them. So with this, we'll go into an example and just try to see how can we use Sparklens, and try to figure out what can we do with an application. So this example came from my friend Sandeep, and so I'm going to walk through this. So in this particular example, we were working with the customer, and the customer basically complained that the application takes a long time. And so when we ran the first sort of run with Sparklens, this is what the numbers that we see. So we see that driver walk clock time is about 1%, which is very good. We don't want too much driver time. Then we see that executor wall clock time is 45 minutes, and so that's 46 minutes. So this is a good start. And then when we go down, we see that the critical path for this particular application is about 7 minutes and 32 seconds. So as we discussed earlier, if the critical path is much lower than the executor in the total wall clock time, it means there is a lot of potential to really uh, in- give more resources and make the application run faster. So this what you see here is the same Sparklens report. In this case, instead of giving it in a graphical manner, what we're showing is more like a textual line by line, simulating that with different executors count, what is the estimated time in which this application will finish, as well as the cluster utilization. So one of the things that you should notice at the top is that Sparklens will also not only just tell you the simulation estimated time, but it will also estimate the model error. So let's say for this particular example, Sparklens noted that we estimated this particular application to finish in 42 minutes, whereas the actual application took 46 minutes. So based on those numbers, it will compute that the model error is 7%. In some cases, there are tricky cases where Sparklens is not able to find really figure out the right estimation. In which case, you'll see that the model error is much larger than 7%. So if the model error is large, you probably should not be depending upon the results. But if the model error is low enough, then the estimates are probably much more reliable. So all right. So basically, what we did here was that we said, okay, because our goal is to sort of minimize the time. We took executor count at 100 to be to be a good value. It is expected that it finish it in about 13 minutes, and with a utilization of 62%, which was something that we could probably live with. So that's what we did. These are some of the experiments that we did. So originally with 20 executors, we got about 46 minutes. When we bumped it up to 100 executors, the work clock time was 16 minutes, not the projected 13 minutes, but still close enough. And then when we increased the max executors to 400, the work clock time further reduced to 9 minutes. Now 400 was probably an overkill, but we just had an experiment to make sure that people know that it's something that's possible. Just to one more thing that I want to add was, why did we increase the min executors to 100? Now, Sparklens doesn't have a model for this. How do you figure out the min executors? But one thing to notice is that if there's a lot of difference between the min and max executors, for example, 20 and 100, what can end up happening is that in the map phase, you can essentially produce a lot of shuffle data. And if that shuffle data is present on only, let's say, 20 nodes in this particular case, and when the shuffles, when the reduced stage starts, and the 100 executors are trying to fetch this shuffle data from only 20 nodes, instead of compute being the bottleneck, the network bandwidth becomes the bottleneck, and that basically makes things slower. So just to make sure that you have enough network bandwidth, it's a good idea to make sure that min executors is also proportionally increased when you increase max executors. All right. So with that, we'll move to example two. This is probably is actually an old example, but it's sort of still worthy and so much to learn from here. All right. So this happened a long time back, and basically there was a POC that we were doing with the customer, and when we ran the application, it took about 158 minutes to complete, and somehow the expectation was that this should finish in about 30 minutes, and so we said, okay, we'll use Sparklens. We got 158 minutes. The problem was the critical path was 127 minutes only. So 127, 158, not much of a difference. And that basically tells us that one thing that we cannot do is adding more resources. So that is not an option. We have to think of something else. So then we started looking at, what are the other characteristics of this particular application. So one characteristic that we noticed was that this had too many stages. So typically, too many stages typically happens when there is a for loop somewhere in the application where something is being repeatedly done. So we wanted to go and find out which part of the code is actually doing it. So we just browsed the code and found out that at some stage the application was trying to write to a Hive table, but instead of letting a parallel write happen to the table, somebody had written a code which was essentially making a list of all the partitions, and for each partition, it was basically doing a write one at a time, and that is what was slowing the whole thing down. So basically, doing it things partition by partition is actually requires more code. So all we had to do is comment 3 lines of code and add 1 line of code, and that's all we did and tested what is the result. So when we do that, this is what happened. So our runtime reduced from 158 minutes to 26 minutes, and we were like, well, our goal was to do it in about 30 minutes, so we were very very happy. But what another thing that we noticed was that the ideal application time in this particular case is just 4 minutes. Now, ideal application time is sort of is a a virtual kind of entity. The way we define ideal application is that it's an application where the number of tasks is, let's say, equal to the number of cores. So there is zero wastage because of Skew, uh, because of lack of tasks. And second, the an ideal application, each task is of the same length, which is the average of the length of all the tasks. So which also means that there is zero skew. So an ideal application is an application sort of virtually constructed in which there is no loss of compute time because of either lack of tasks or because of scale. So that gives us, sort of an upper bound on that. If we were to create a perfect application, how much faster it will run. So in this case, this number was 4 minutes, which was really low. So we sort of tried to investigate it a little further. So this is what we find out. So one of this ECCH is uh, executor core hours essentially, and so what we found out was that about 91% of the compute time was actually getting wasted. So that was really high. So we sort of tried to debug it much further. So Sparklens also tells you stage by stage how much wall clock time did that stage take. So when we were going through that list, we found that stage ID 33, for example, represent 85 or 86% of the wall clock time. So that's the only thing that we can focus on, and if we fix that, we'll get a lot of value. Now, the thing that we noticed in the stage ID 33 is that it only had about 10 tasks. Now, usually this application was running. This application was actually running on a 100 node cluster, where each executor had about 8 cores. So 800 cores were available. So with 10 tasks, there was no way this application can really use the cluster that well. So when we started looking a little deeper into it, we found that in the code somebody had written a repartition 10. We don't know why, and maybe it was like they were trying it on local machine, and that's when they do it. We don't know, but that was the cause of not having enough. Only creating those 10 tasks. So the change that we made was that okay, we don't need it. We need as many partitions as we need. So we removed that, and since we had 800 cores and the Spark SQL shuffle partitions by default is 200, we change it to 800 so that there are enough number of tasks that are available, shuffle tasks, sort of reduced tasks available to use all the codes. So basically, those were the total three changes that we made in the application during debugging. And this is the final result of this particular application. The total wall clock time came down to just 9 minutes 48 seconds from original 158 minutes. And the critical path at that point was about 7 minutes, and the ideal application was again 7 minutes. So at this point, we noticed that this is what we are doing is pretty good. Maybe we can do a little bit of improvement, maybe reduce the number of resources, and go a little bit away from the critical path if we want to optimize it further. But as far as latency is concerned, we had achieved a pretty good result by making three changes, almost guided by Sparklens. All right. So with this, I'm almost at the end of this presentation. So I'll summarize what we have learned so far. When we look at optimizing a Spark application, we should look for three kind of wastages, compute wastages, which are caused by driver, skew among the tasks in a stage, or the lack of tasks. And all these things can be easily found by using Sparklens. So Sparklens will make your profiling or your performance optimization more as a process than as a trial and error sort of method. The second thing, the other thing that I want to tell you again is that Sparklens is very easy to use. All you need to do is put two configuration options, and you can use it. And you can use it anywhere. There's no install, there's no download, nothing. Everything that happens automatically. Just set these two parameters. And if you would like to, instead of a console report, you want a HTML report with a link, then just set your email address, and you should be able to get a full report and use Sparklens easily. And finally, Sparklens is open source, so you can if the current form of Sparklens doesn't work for you, you can go and change it the way you like, and make it work for you in a way that makes sense to your project. And that's all. Thank you so much.